All right, cool. First, I want to thank Sean for organizing this tonight. Getting the speakers and the space is a huge help for us. We appreciate that. I work at a company called Calibration, and we are a small venture-backed company, about 13 employees right now, about 6 engineers in the team, and we deal with mostly healthcare providers and organizations. And what we do is we kind of empower them to just do some patient discovery on some linked data sets, and also allow them to kind of just mostly do patient discovery on other data sets in healthcare organizations. Small team. Right now, we're kind of using a lot of Python and Scala, but we're not afraid to try new things. But with that, we're also not afraid to kind of throw things away if they don't work. So looking for a wide range of openings, even like product management, operations, software development, data scientists. So looking to work for a small, fast-paced growth company. Let me know. I'll be around tonight, tomorrow, not tomorrow, tonight, and online. You can hit me up at peterbryant@healthberry.com or at business cards I can give to you tonight. In regards to DataPhilly, we have one other announcement. Next Tuesday, we're having a hackathon at Industrious. It's on the meetup page, so please, if you're free or want to join, look at the meetup page for more information, and we look forward to seeing you there. From what I hear, the last one was a big success, so looking forward to continuing that as we go forward. So, thanks, Sean. Great.
Thanks, Patrick. And I can't project well as Patrick can, so I need the microphone. And so next, before introducing the speakers for this evening, wanted to introduce Mike Becker, who is one of the co-organizers of DataPhilly. Oh, we're good? Okay, we're good with announcements? All right, so then it's me. So my name is Sean Brio, for those of you who don't know me, and if this is your first time at DataPhilly, again, warm welcome. We typically do a speaker series once a month where every month we invite a couple of speakers to talk about a different topic related to data science or software engineering. The common theme is just data. And we've had a wide range of topics from data visualization and art inspired by data to tonight, which is a very different theme, which is neutrino physics. And the reason this came about was we were looking for a big space because space is generally a problem with us. We're a very active group. And I thought, well, the main auditorium here in the physics building at Penn has 220 people. This would be a really great venue for the August meetup. And the department head was very enthusiastic about the idea. He just suggested that it would be a good idea to let people in Philadelphia know that Philly was intimately involved with the Nobel Prize of Physics that was given last year, 2015, on the discovery of neutrino oscillations. It was given to 2 experiments, one called SNOW in Canada and another one in Japan. And you'll learn more about this experiment called SNOW in Canada, where Penn was intimately involved with it. So from a data science perspective, in terms of learning what the Philly community is about, what Philadelphia has been involved with historically, Penn in Philadelphia has historically played a huge role in the discovery of neutrino oscillations and the 2015 Nobel Prize in Physics. And it's with that reason that tonight turned into a neutrino physics themed event. And so we have 2 speakers to talk about neutrino physics. It's completely coincidental that neutrino physics is also my background, but that's neither here or there. That was complete coincidence. So the first speaker I want to introduce is Nuno, who is from Portugal, and he did his PhD in Lisbon on analysis with the SNOW neutrino experiments in Canada. And he'll talk about his PhD work tonight. And after finishing his PhD at SNOW, he went to Germany and Dresden to do his postdoc on the Goethe experiments. And after he finished his first postdoc there, he came to Penn and lived in Philadelphia for about 3 years now, right? 2 years. working on the follow-up to SNO, which is called SNO Plus, and the deep underground neutrino experiments that's being constructed right outside of Chicago called DUNE. So with that, and then after Nuno will speak, we'll hear another neutrino experiment talk about just detecting neutrinos at the South Pole with IceCube from Richman. So with that, thanks, Nuno.
Okay, so thanks, Sean, for the introduction. As Sean mentioned, my name is Nuno, and I worked as a PhD student in the SNO experiment. And so I'm going to talk, this is more a high-level talk, and I'm going to talk about the Sudbury Neutrino Observatory and try to give a little bit of information about how we performed our analysis and how that ended up panning out in the discovery of neutrino oscillations. So before going into neutrino physics, let me make a disclaimer. SNO is what we would call now a Nobel experiment. First, it started being designed in the 80s. And we took data between 2000 and 2006. We finished our analysis in 2012, and by then we were, usually physics experiments have one thing, is that they behave like a Gaussian. They increase the number of people involved, and then they reach a peak, and then they start to decrease. So 2012 was really the tail of the Gaussian already. So we actually had pretty little manpower, and at the most, at the peak, we had about 120 members, which is nowadays is pretty small by comparison with other experiments. One thing that you have to be careful is that talking about data analysis, well, I'm talking about something that for us, having a computing farm with 100 cores was gigantic at the time. And more important, actually a good part of our code is written in Fortran. Well, welcome to the 80s. Another thing is that, well, we were basically, being a physics experiment means it's always in development. So when we say that we did this kind of analysis, well, that analysis evolved since for a long time. So when I say that we did an analysis in some specific way, actually the techniques evolved and we used different techniques. And I can give you more details about some of those techniques if you're interested. So let's talk about then neutrinos to start, and well, what are they and why we would care? So start with this. So everything that we see is made of three particles: electrons, protons, and neutrons. This is a small schematic of a carbon atom, and you have the electrons, the protons in red, the neutrons in white, gray. So this means that buildings are made of these three. You are made of these three particles. The world is made of this. But now here's the question. What about the whole universe? Is it made of only these three particles? Well, no, not even close, not even remotely close. Thing is that for each of these three particles that we have in the universe, we actually have 1 billion neutrinos in the universe. Every cubic feet has, well, 10 million around. So we could say that we are actually made of dust because we are very, very small indeed. So neutrinos are actually produced in various places. So, for example, they were produced on the Big Bang. They are produced in the Earth, nuclear reactors, that's one of the artificial sources that we have. Particle accelerators in the stars. The whole process that the stars work actually produce neutrinos. So this means that our sun is actually a very powerful source of neutrinos. So neutrinos produced in the sun because Sudbury Neutrino Observatory was focused on looking at neutrinos from the sun. So coming from the sun, neutrinos from about 93 million miles take 8 minutes to do so. And at any moment, we are being crossed by this amount of neutrinos from the sun. So per second, the sun produces 10 to the 38 neutrinos. So that's 1 and 38 zeros right after it per second. And basically, the whole mechanism that the sun works, it produces energy, light, that we see, but part of a byproduct is neutrinos. So this amount of neutrinos come from the whole fusion reaction that happens in the sun. And so this means that without neutrinos, the sun would not shine. So if we want to understand the sun, we have to understand neutrinos. Actually, we can expand because the sun is a star. So if we want to understand the universe, we do have to understand neutrinos. So let me talk, since the goal of Snow was to work on the Solar Neutrino Problem. Let me explain what is the Solar Neutrino Problem. So what do we know about neutrinos? So they are very, very light. So light that we still don't know exactly what is its mass. And for decades, they were thought to have no mass at all. When they were postulated, theoretically, they were postulated as a no mass particle. They are also very small. So I'm not going, you can see the number. And they exist in 3 families. We usually tend to call them flavors. They exist in the electron flavor, muon flavor, and tau flavor. And the reason for this flavor is because they actually pair with another kind of particle. When one of these particles is generated in the decay, usually a neutrino accompanies it. So another thing that we know about them is that they interact very, very weakly. This means that a neutrino produced in the sun can go through 1.5 light years of lead without interacting. If you think about any other particle of the same energy, it would go a few centimeters at best. A neutrino goes through light years, so they interact very, very weakly. So if we want to see neutrinos, so what do we need? Well, we need a very intense source. The sun seems a good candidate, and we need a really big particle. So what do we know about solar neutrinos in particular? Well, in the sun, they are produced in a single flavor. They have 3 families, but they are producing only one of them there. The reason has to do with the energy of the fusion reaction in the sun. And they are produced actually very close to the core of the sun. So since they interact very weakly, seeing neutrinos actually tells us how the sun works on the inside. And that's our only probe that we actually have of the sun interior. The only direct probe, let's say. And well, as I mentioned, they are really produced in copious amounts. So how do we see solar neutrinos? Well, let's start by digging a very deep hole, or get one already done, not mine. Then build a gigantic target. Instrument it, because you want to see something out of it. Take data for several years, and yes, you always need several years, because otherwise you won't see anything. Collect, analyze the data, find neutrinos, understand them, understand the sun, go to Stockholm and get a Nobel Prize. So actually, this recipe pretty much works. Ray Davis just followed that recipe. So if you use 600 tons of cleaning fluid, installed 1.5 kilometers underground in a gold mine in Homestay, South Dakota, and the idea was to detect neutrinos by observing an argon atom that was produced by the interaction of neutrino with chlorine of the cleaning fluid. So the neutrino would interact with chlorine and it produced an argon atom. This atom is actually radioactive. So by seeing the decay, the radioactive decay of the argon, you would say, I saw neutrinos interacted here. So I saw solar neutrinos. So if our understanding, and this number is important, if our understanding of neutrinos and our understanding of the sun is correct, we should have seen, well, this is average over the time of running 1.5 atoms per day, which already tells how little neutrinos interacts. So he actually got a mixed result. He did see neutrinos, and he did get a Nobel Prize. Problem is, he only saw 1/3 of what we should have seen. He saw 0.48 when 1.5 was expected. And this is actually the result shown by the experiment. And you can see clearly the expectation was way higher than the observation. So, what's going on? Well, the most immediate answer is the experiment is wrong. Another one is, well, could neutrinos behave differently from what we expect? Could the sun actually work differently from what we expect? Or there were actually quite a lot of exotic suggestions, and one of them being that the sun was dying, because when the sun is, well, eventually the sun will die. And when it happens, the number of neutrinos produced will decay, will go down. So if the sun died, if the sun was dying, we would see less neutrinos. Actually, this Arthur C. Clarke wrote a novel about precisely this hypothesis. And so this is actually the solar neutrino problem, is why do we see only 1/3, well, why do they see only 1/3 of the neutrinos that should have been seen? So enters the Sudbury Neutrino Observatory. So the solar neutrino problem was basically hanging around without a solution for almost 3 decades. So 20 years, a bit over 20 years. And several other experiments confirmed the home state results, but none of them actually explain that deficit. So they basically confirmed the problem, but did not find a solution. And then a professor, Herb Chen in UC Irvine, he proposed an experiment with, well, the principle is the same, but using heavy water instead of cleaning fluid or normal water, like another experiment. And he proposed this actually in '85. So the advantage, one thing that made this experiment quite interesting, that it was an inclusive experiment. Heavy water is special when it comes with respect to neutrinos because there's different ways that neutrinos can interact with it. So this means that, and each of those ways is actually sensitive to different phenomena, to different kinds of neutrinos. So this means that we could have different sensitivities within the same experiment. So we could have some disambiguation there. So we could actually be sensitive to different flavors through the different reactions that could happen. Problem, heavy water is a rare commodity. Very rare, actually, because it's produced in nuclear reactors. Solution, well, Canada does have a lot of it because they have a type, they use CANDU reactors, and those reactors use heavy water as a cooling mechanism. So, how to see neutrinos? Snow model. Again, dig a very deep hole. In our case, we found one already there. Even deeper than HomeSec. Convinced the Canadian government to lend us all that heavy water, worth at the time about 330 million Canadian dollars, and they did lend us for $1. That was a very good deal. Build a gigantic tank to hold the heavy water, instrument the tank again, fill the tank, insulate a little bit more, collect data, look at the data, solve the solar neutrino problem. And we did just that. So let me tell about the Sudbury Neutrino Observatory. So it is located in the Creighton nickel mine in northern Ontario, so in Sudbury. It's located at 6,800 feet underground. So it's deep, it's quite deep. It has an acrylic sphere of 6-meter radius. So this is a schematic of the detector. This whole thing is constructed. So 2 kilometers underground. We have an acrylic sphere where we put the heavy water, and then we filled everything around it with normal water, pure, but normal water. And this acts mostly as a shield for radioactive backgrounds around. And then we have the whole volume surrounded by light sensors, about almost 10,000 of them. So as I mentioned, snow had the advantage that it could see neutrinos in different reactions. So those reactions are called charge current, or CC, neutral current, or elastic scattering. So the way the signature of all these is actually quite similar, but they are sensitive to different things. So charge current is sensitive only to one flavor of neutrinos. The neutral current is sensitive to all flavors equally. And the elastic scattering is preferentially for one flavor, but is also sensitive to the others. So how do we detect neutrinos in heavy water? Well, we see, so neutrino comes, and for example, in the elastic scattering, it hits an electron, it kicks the electron away, and the electron will produce shrink of light. Shrink of light is basically is a light effect similar to a sonic boost. That is, if the particle goes sufficiently fast in the medium, it actually emits light that goes in a cone. And that's pretty much what you see here. The electron is kicked, and it produces light that then we detect on our photon sensors. Charge current reaction is pretty much the same thing. What happens is that it interacts deeply with the deuterium on the heavy water, and it separates the protons, it basically disintegrates, transforms the neutron into a proton, and that emits an electron that we then see again. Sorry. And then we have the neutral current reaction, which is slightly different because this actually photo disintegrates the deuterium, which means that we don't see a shrink of cone of the electron directly. What we do see is actually the neutron that eventually is captured back, emits another particle, and we see it. So it's an indirect measurement. And this is important because this means that we have to look for a different particle here. So we could look solar neutrinos in different ways. We could be sensitive to one family through one reaction, to all with a slight preference on another reaction, and no preference in a third. And for the first time, we could answer the following questions: how many neutrinos from the sun do arrive on the Earth? Because the other experiments were all sensitive to only one family of neutrinos, because they assumed since the sun produces only that family, why would we try to look for any other? That should be enough. But this was the important part. And actually, the fact that we could be completely insensitive to the flavor made that we actually broke the experiment into 3 different phases, each one having a different way of seeing that neutron particle that was produced. So just a little bit of pictures. So this is actually the Creighton mine in February. And yes, there's always snow there. The original surface lab, yeah, we started on containers, pretty much. Then we were upgraded to something like this. The container is still on the back. We now do have a slightly better lab. Underground, so this is a working mine. We actually have to do all the trainings that miners have to do to work there. And it's pretty dirty down there, except inside of the lab that is actually one of the cleanest places on Earth. Our control room, it did evolve during time, and that's because these ones were really a nightmare to work with. So, and this is just some pictures of the detector. So you can see the acrylic sphere, the photon multipliers, the sensors. So at this point was only partially being assembled. This is the whole thing already built, ready to fill with water. So these are a series of panels that are shown here, and then each of these models is actually a photon multiplier, which is this, a light sensor, and a reflector assembly to increase the light collection. And we managed to get some pretty nice pictures there as well. So we did see solar neutrinos, and this is basically what a solar neutrino looks like in snow. You have, as I mentioned, stream of radiation goes in a cone, and basically this is the pattern that we would see when the neutrino interacts, produce a light cone, and you get a pretty clear, well, this already had some work done on it, but you get a quite distinctable cone. So saw a few candidates, depending on where it locates, can look a bit different. We also can see other particles, like cosmic muons, which is a completely different particle. We don't care about it, and luckily it looks very different. So it allows us to basically put it aside, throw it away, and nope, we won't look at it. We also can look at atmospheric neutrinos, which are also important. They are not produced in the sun, they are produced on the atmosphere in the Earth from cosmic rays interacting on the atmosphere, and for us is also a background. So, but as you can see, they actually do look quite different, so we cut them rather easily. And one thing is that since snow was so deep, the amount of these that we would see is relatively low. So how do we analyze that in snow? So part of the challenge of the data analysis was what we have, or what we call the raw observables, is that we have charge on photon sensors, and we had time on each of these photon sensors, and then we had the photosensor position. And this is all we had. And then we had to work from this to build something where we could actually get physics out of it. Another problem that is quite specific, especially in snow, because we have these three different reactions, that there's no clear event signature. When I showed this event just a moment ago, something like this, we have no idea by looking at this event if it is which of the three reactions is actually producing it, because they do look the same. So this is one of the biggest challenges that we had to deal with. And so the ones that we could really identify, they were very clearly identifiable. And those we were not really into, so we put them aside quite easily. So eventually, basically, our problem is that we are looking for a needle in a stack of needles that looks like every other needle. So we do need to find some way. Another challenge is that this is what we got when we look at the data without doing anything on it. This is what we would like to see. There's more than 2 orders of magnitude difference. Thing is, there's a lot of background there that we have to basically get rid of. So our analysis chain was basically first doing the data processing, which basically removes most of the backgrounds. We reconstruct position and energy. Position and energy are physical quantities that for us allows us to extract the physics, unlike charge and time. And then from there we have a background measurement. We build a physics model for the interactions. And from these two, we then build what we call the signal extraction, which is basically extracting the physics out of this data. So cleaning the data basically means applying a series of cuts. We did time cuts, coincidence cuts. We have instrumental backgrounds, so this means the electronics and the photon sensors themselves will create backgrounds for us. Pickup. So we had several series of cuts, and that just by applying these cuts, we got from here all the way to this purple line, which now it's much closer to what we would like to get. Another second step was we have to reconstruct the event. And this means converting from photosensors, the PMT signals, into physics observables. So we start with position that we get from the pattern, the time, the charge, and from this we want to get something that tells us the physics of the event. Its vertex, so basically its precise position of origin, its direction, its energy, and isotropy was one specific variable. The way that we do this is actually by using specific filters. So we model the interactions, And basically, each of these filters had their own estimator that we basically built out of it. So these were basically estimators that we were put into the analysis to obtain the physics. And all of them pretty much depend only on one of those raw observables that we have to begin with, or on some other parameter of the detector that we obtain through some other indirect method. So how do we do the analysis? Well, first, understand your detector. Important. Model each event type in your simulation. This is basically how we basically went through it. Then predict how the interesting events, or interactions, should look like in our detector. And then compare your prediction to the data, build a figure on merit, change some assumption, compare again, and keep doing this until you no longer improve. And when you get that, you extract out of it. What is the issue on this analysis method is that you really need to nail down these two first ones. You will need to understand our detector very well, and we need to be able to model everything in our simulation. So understand the detector. So we need to know how well the detector measures these three observables. So the solution to do this is calibrations. Some, well, different experiments deal with it differently. In snow, our global analysis in itself, our final analysis is not extremely complicated. But we spent a gigantic amount of time calibrating the detector. So when we went to the analysis, we really knew how the machine actually worked. So we did have a calibration system that allowed us to place well-known sources, and this is important. These were different radioactive sources. Not all of them were radioactive. We did have also some light sources. And we placed this through a mechanical system in the detector in different positions, and we would see how the photon sensor would look at it. And each one of these analyses had their own analysis method. Some were more advanced than others. For example, the optical calibration was rather interesting analysis. I worked on that one. We had usually about 500 free parameters and 5 million points, so which is not a lot. So the thing for us is that we spent about 90% of our analysis effort was actually doing this, doing calibrations, analyzing the calibrations, seeing how the detector works, rinse and repeat. And the thing is that the signal extraction itself, so the interpretation is quite standard. And when we actually did improvements to it, most of the time they were driven by improvements that we performed on the calibrations themselves. It was always calibrations that drove. So this is just the calibration system, how it went into the sphere, and this is basically the coverage of the planes that we could cover. So lots of calibrations. Step 2, model the detector in your simulation. Well, run the process many times. So basically we use a Monte Carlo simulation, which I think everyone is familiar with. We run the processes, the different processes that we plan to have, that we think we have in the detector. Many times we randomize the inputs that we don't know precisely, and this includes properties of the detector and the underlying physics. The way to actually model the detector, again, is through the calibrations. The calibrations provide both ways of measuring properties of the detector and ways of tuning our simulation itself. And the idea is that this effort of correcting our simulation to match the detector ran for 8 years. We always kept improving it. So this is actually some of the results that we got on the Monte Carlo, and you can see, so there's 2 sets of points here, and one is data, the other is Monte Carlo. This is a calibration source. And you can see the match that we could reproduce exactly what we put inside the detector. We could predict exactly in our simulation. This is this is for one of the observables. This is actually physics data. And this is actually for different radiation sources. The black lines are the prediction for Monte Carlo, and the points are data from calibration sources. So let's assume our simulation is in good shape. Well, let's predict the observables. So we chose a series of observables, of physics observables. Usually we could use only one. That's common, fairly common. We actually chose 4. And the reason is that since we have 3 different reactions and none of the observables is really unique in a way to distinguish the different reactions, we built a fully multidimensional model. And you can see that each of these different observables actually has a good handle on one of the reactions. So for instance, the angle to the sun, of the event to the sun, has a good handle for elastic scattering events. The isotropy has, here is not so visible, but actually the isotropy has a very good handle on the neutral current events. This is a bit misaligned, well, very good, somewhat good. And the energy is particularly important to look for charge current events.
I have a question.
Yes?
When you talk about events, do you mean each detection?
Each interaction. Okay. So these are basically probability density functions. We run simulation over predicting millions of events of elastic scattering, and then we look how do they look in this observable, in this observable. So that's what our simulation is for, is to basically build. So these are these are projections. What we do is we predict from the 4 observables at a single time because you have correlations. And to deal with the correlations, we actually do a full multidimensional fit with full multidimensional probability density functions. So, general approach for the signal extraction. Well, so by now we cut out most of the events that we don't care. We model how each type of events behave in the detector, as I just showed before. And we do have an idea how to better distinguish the events because we already chose our observables. So what we need to do, well, we need to evaluate for each event what is probability of it being in each of the 3 kinds of interactions. The thing is, our handle is too weak for each of the different kinds that we have to really group all the events and make a direct fit for data. We can only do statistic separation. We can not really do event-by-event separation. So we perform our analysis, as I mentioned, is rather simple. We perform an extended maximum likelihood fit. We don't have that many events, so with that, we always assume that they are Poisson distributed. And we build our probability density functions for each of the observables and for each of the signals, and the signals being the 3 classes of events and then background events, because there's always radioactive backgrounds. We try to keep them to a minimum, but so I'm going to skip a bit over this. This is actually data projected from that. So the PDFs are 4-dimensional, but then at the end we basically project them, we marginalize them to see how the different classes of events are sensitive to each of the observables. And as mentioned, so the best handle on the S, you have a slight sensitivity for charge current events. The isotropy basically separates the neutral currents because neutral current events are basically, they produce a neutron, so they spread more. So we actually have the heat distribution on the photon sensors basically is more wide. The radial distribution, this is mostly to cut out radioactive backgrounds because they don't come from the detector, they come out from outside the detector mostly. And then we have the reconstructed energy. This is particularly good for the charge current events. So we do the multidimensional fit. We had about a few thousand data events, about 10,000 per phase. So we have 3 phases, that makes about 50 free parameters with correlations. we use the multidimensional PDFs to account for those correlations. Well, correlations within the observables and between observables. And in fact, to control systematic uncertainties, we actually fit some of them along with the observables themselves, especially energy-related uncertainties, because they have a strong correlation. And this is, after running for about 2 years, this is what we got. And so this is the on-stake experiment and their result. And that's about 1/3 of the expectation that was. Snow, through the charged current reaction, actually is very consistent with the Calorimetric experiment. But the neutral current reaction was bang on the solar prediction. So that's pretty much what we really would like to have seen. And if you compare with the other experiments at other times, they had sensitivities to different reactions, but in the end, it was this neutral current reaction that ended up explaining what was going on. So what did this imply? The fact that we see very different interactions on these two different channels. Well, we know that neutrinos, only electron neutrinos can be produced in the sun. So, but we see way more neutrinos if we don't select just by electron channels. So this means that neutrinos have to change flavor between being produced in the sun and actually arriving in the Earth. Neutrino oscillations. So why do they change flavor? A bit of physics explanation. Well, if electron neutrino is not really a particle, but actually a combination of states, quantum mechanics allows you to do that. So how can we still see an electron into a muon? Well, the electron neutrino does not exist to be true.
Can other stars produce neutrinos, not just the sun?
Sorry?
Can other stars produce neutrinos, not just the sun?
Yes, but that's something why the elastic scattering experiment is also very important, is because it correlates directly with the direction of the sun. So one of the reactions, or one of the 3 reactions, is basically a purely scattering interaction. So it's really it's a kinematic effect. A neutrino comes, kicks an electron, the electron goes, like billiard balls, pool balls. And so what happens is that we could clearly see a correlation with the events that were selected for the elastic scattering reaction and the direction of the sun. So that gave us that extra. So we could tell that neutrinos, there's other effects that we could cross-check. The fact that we saw the amount of neutrinos that is actually consistent with what we were predicting on the 3 full neutral current channel. And there's another effect, is that we were looking for an energy range of neutrinos that we didn't really have a source nearby that could justify it, because we were looking for relatively high energy. From an Earth perspective, too high. From an atmospheric, it was too many neutrinos. So it was really, by exclusion, we could still correlate fully with the sun.
I think he was asking whether all stars, not just the sun, produce neutrinos.
Well, all stars produce neutrinos. It's part of the fusion. It's part of the fusion process. So the thing here is that all stars are way farther away from the sun, and since they produce isotropically, their flux reduces at the Earth, reduces with the square of the distance. So the next closest star to the Earth, it has a very small contribution. It's pretty much discounted. So if an electron neutrino is not really a particle, but a combination of states that is with some different proportions, we can assume that if those states have mass and those masses are different, they propagate at different speeds. So if you produce neutrinos of electron flavor, this means that you have a soup of a certain portion of muons, U2 and U3. Now, neutrinos come from the sun to the earth. That's quite a long distance. Those speeds are going to change. They are going to get in different phases. So this means when we detect something here, they will come on different phases, which means they will have different proportions, which will mean that they are no longer electron neutrinos, but some other flavor, for example, a new mu. And that's effectively what neutrino oscillations represents. It's a quantum effect in which if a particle is basically a superimposition of different states, if they have a mass, if those states have different masses, they will propagate at different speeds. And that's why neutrinos changing flavors between production in the sun and detection on the Earth implies that neutrinos do have mass. And that's basically what got us the Nobel Prize in Physics. And I quote, for the discovery of neutrino oscillations, which shows that neutrinos have mass. So, great, we got a Nobel Prize many years after we stopped taking data. So the first analysis was really a success, but we actually did not sit idle. We did keep collecting data for 5 more years, and we did improve our analysis, not only through the calibrations that I mentioned, but we actually implemented several other analysis methods, some of them redundant, and some of them actually brought some interesting new results. So in one of the latest one, we implemented a Markov chain Monte Carlo, which is completely consistent with the maximum likelihood that we use. We did implement a kernel estimators analysis, which was, this is also, I also found, thanks to Wikipedia, I found that this is also known as through a different name. And the interesting part of this is not only the method itself, is that we actually implemented in CUDA. So that was implemented here at the University of Pennsylvania. We have a couple of Teslas, 4 of them, and that's enough to actually speed up our analysis by 10-fold on this kernel estimators. We did do some pattern recognition, and that was for something that I didn't mention, is one of the specific phases of snow. And we also, and this was mostly a part of my thesis, was actually parallelization, because we do have a gigantic likelihood space. And so one way to tackle with it is actually, if they are, the different points in the likelihood are sufficiently independent, we can split and tackle different regions separately and then build a whole likelihood space again. And you also lowered our energy thresholds. So what are next steps for, what were the next step for snow? Well, the laboratory was actually expanded and into one of the deepest physics laboratories in the world. Is now Snow Lab, that hosts actually several experiments on different topics. The detector itself, the machine, was overhauled into a new experiment, and now is looking for a whole different set of neutrino properties. This is Snow Plus. We returned the heavy water because it came for free as a loan, but we did have a pretty big insurance on it, and that was expensive. And well, thanks to the Nobel Prize, we actually picked up analyzing the snow data all over again. So we are back to looking at Fortran code, which is not so fun anymore. But now, instead of looking at just solar neutrinos, we are looking for more exotic physics, still neutrino related, but other kinds of physics. And it's quite active, the group, nowadays. So one reason also why we picked up the analysis all over again is that nowadays we have so much more computing power than we had back in the day that we can do way better things now. And because the thing is that even most basic computing farm, even the one that we have here at the University of Pennsylvania, is pretty much as powerful or even more powerful than all the computing resources that we had back in 2001 when we were doing the first analysis. So that's pretty much it. And this is the SNO collaboration pretty much at this peak. Any questions?
We have time for a question or two if anyone has anything pressing on their minds.
I have a general question. Why do you care to put your detectors at the bottom of a line? Because if deuterium is the one capturing it, why do you care about
Because of mostly cosmic rays. You have cosmic radiation. That we basically had about 70 events per day from cosmic radiation. And that's nothing. You have right now here you have millions. Just on you, we now imagine of something of 12 meter diameter. We would be completely taken over. So usually experiments that work on the surface, there are not that many neutrino physics experiments on the surface. And the ones that do usually have some other mechanism that they can cut out and they can afford to run for longer to have some sort of coincidence. If you're looking for something like a natural source when you don't really know when an event is coming, can come at any moment, you have to go deep, because otherwise the cosmic radiation just destroys any.
Is the detector in Japan similar?
Yes, so that is the other part of this Nobel Prize, is supercanyon. And they looked, so SNO looked at solar neutrinos, so neutrinos coming from the sun. Supercanyon looked at, well, they did also look for neutrinos coming from the sun, but they are only sensitive to the elastic scattering connection. But there gave great advantage looking for neutrinos produced in the atmosphere. And the thing is that they could basically correlate, because elastic scattering is highly directional, they could correlate the direction that it comes, so they could actually model the flavor change with this industry. So that's actually, they saw the oscillations before we did. They saw it in '98, we saw it in 2001. But since both experiments saw it through different methods, one basically cross-checked the other. And it's a bigger detector. Significant is like 50 times bigger. But it's also much closer to the surface, and it's normal matter, not heavy one.
Any other questions? Great, thank you everyone. So while the speakers are switching up here, I have one more announcement. Next Wednesday is the super meetup. It's run by DataPhilly, and it seems like a lot of you may have RSVP'd on our page. Apparently, if you want the free beer at the event, you need to RSVP on the DataPhilly page. It is linked to from our meetup group. So if you accidentally RSVP to our group, make sure you RSVP to the DataPhilly group. And I hope to see you there.
How do I enter full screen? I forgot I enter full screen. There we go.
Actually,
Enter full screen.
slideshow. I think slideshow actually projects it, not here. Projects it there. No. There we go. Cool. Now we want this. Yeah.
Okay, so
Yeah, this is probably the best one.
okay, so from neutrinos from the sun, what can you do if you want to crank it to 11 and look for neutrinos coming from outside of the solar system? As Nuno mentioned, you have to go bigger. You have to build something bigger, and you have to go deeper. And so the next step to look for neutrinos outside of the solar system is to build a giant array at the South Pole called IceCube, which Mike Richman will talk about. And Mike Richman is a PhD student at the University of Maryland College Park, and where he look for neutrinos coming from gamma reverse, which are some of the most violent known explosions in the universe. And he is now a postdoc here at Drexel University across the street. And again, this kind of obscure physics topic is an important part of the research that's done here in Philadelphia that all of you are a part of. So just before I segue, before I introduce Mike, a little bit of a vocabulary translation, which may or may not be helpful to the data scientists in the room. Every physics experiment, for data scientists here, every physics experiment starts as a time series of voltages. So every physics experiment from a data science perspective is just a time series analysis. And all machine learning that's done, all statistical analysis that's done, the time series analysis methods for the most part. And also, we talk a lot in physics about reconstruction. We've heard that in Nuno's talk, and then Mike will talk a little bit about reconstruction. All that means is feature extraction from a data science vocabulary perspective. So hopefully that helps. So with that, I'd like to introduce Mike.
All right, thanks. Let me just get this thing clicked on. All right, can you hear me? Okay, cool. Yeah, so I'm excited to come and see DataPhilly for the first time and speak on machine learning and data analysis for the IceCube Neutrino Observatory. So my story is actually going to start with cosmic ray astrophysics. So a little bit different starting point, but we're going to see a lot of similarities as we go through this slide stack. So cosmic rays are a century-old mystery. In 1912, Victor Hess was trying to figure out what was going on in a tabletop experiment by going and studying elsewhere, like up in the atmosphere in a balloon. And what he found is that of ionizing radiation as he got further away from sea level, to the point of 3 times larger when he got to about 5 kilometers up. So this led to the conclusion that this radiation must be coming from the upper atmosphere. Since then, cosmic rays have been studied by numerous experiments, and we've learned quite a bit about them. So it turns out that these are charged particles, either protons or heavier atomic nuclei, coming from outside of our atmosphere. And their behavior, if you consider their, let's say, oh, this is the weak one, sorry. There we go. So if we look at the rate of observations as a function of the energy, we see over a factor of 10 to the 11 or so in increasing energy, very consistent behavior in the rate of observation. In particular, it's like the rate goes as e to the minus 2.7 or thereabout. And so we think we sort of understand the lower energy of these particles. They seem to be identified with either solar emission or at slightly higher energies, galactic emission, like maybe there's some signs that supernova remnants could be involved here. But for the highest energy cosmic rays, the sources are not yet identified. But there is some theory for them. So the cosmic rays, which again, protons or heavier nuclei, are thought to be accelerated in violent astrophysical objects, like maybe GRBs, or actually, I don't know, there's not that much hope for that anymore, thanks to my thesis, etc. But we were hoping that might be the kind of thing. Anyways, if these protons are being accelerated in these violent environments, then maybe a proton goes and finds a photon, and then you have some particle physics, and then you either get a proton and photons back, or you get other stuff, including neutrinos. Now, we can try to go and look for those photons, but they're going to be attenuated by cosmic microwave background radiation. That is, they'll find other just ambient photons in space. And so they won't get to us. The cosmic rays and charged particles can travel further, but not in straight lines due to their charge. They're going to travel in curved paths through space because of magnetic fields. So that brings us to neutrinos, which can travel very long distances, largely unencumbered by any intervening matter. This is less true at the most absurdly high energies, but it is still true. And so that brings us to the IceCube Neutrino Observatory. So we're talking about big detectors. This is the biggest one so far. So we're looking at 1.5 to 2.5 kilometers deep in the South Pole Glacier. Basically because you might ask why the South Pole. Building big water tanks gets more and more expensive the bigger the tank is. And so South Pole just has like a lot of ice. So you go there, it seems like it's gonna be really expensive, but there was always some infrastructure in place, so it kind of makes sense. So you go there and you build this array of over 5,000 digital optical modules, or DOMs, arranged on each of 86 strings. The total instrumented volume is 1 cubic kilometer, and the detector was built between 2005 and 2010. I'll point out over here the transplanted Eiffel Tower, as opposed to like a person like you might normally see for scale. I don't know how it got down there. Now, unlike in snow, we have some pretty distinct neutrino detection signatures, so we can tell exactly what's happening on a per event basis for the different flavors of interactions. Nuno did me a big favor in explaining what this kind of jargon means, so I don't need to dig into it too much. But what I can point out is that when you have the electron flavored neutrinos, or any of the neutral current interactions, for IceCube, you're just going to detect this ball of light. It's going to be not that much directional asymmetry. That's because there's a lot of scattering in the ice, and so by the time the showers range out, the light is kind of just going everywhere. The only place where you get like a very distinct signature is for the charged current interactions of muon neutrinos, where you get this elongated track. And these are great for looking for sources, at least in principle, because you can tell more or less where they came from. Much more than with this case. And lastly, this is kind of the last thing I'm going to say about the new taus, but if you could see a tau neutrino, there would be a huge initial cascade, and then very shortly thereafter there would be another cascade, because taus have a very short lifetime, so they decay immediately. The cascades are not even distinguishable at lower energies, but maybe at the highest energies you can distinguish them. We've actually never seen one of these. So these are data events over here, but this guy is from simulation. We had to fake it. So those signals in those pictures I should have mentioned were color-coded by timing. And so what's happening there is we have each individual digital optical module, or DOM, includes a photo multiplier tube, PMT, plus a computer, digitization electronics, all housed inside of a glass pressure vessel that can withstand 2.5 kilometers of ice overburden. So the PMT is going to collect the Cherenkov radiation from particles that are moving near light speed. And if there's a trigger condition, which the individual DOMs can actually communicate to each other about, then the digitized waveforms are sent to the surface via this penetrator cable, which is over here and doesn't break the seal of the glass. These signals are then sent up to the IceCube lab. So this is a picture one of our winter rovers took. When it's night, you get some pretty amazing auroras down there. You could also call this sort of like a counting house. The wires all run up here, and then there's a cluster and some other electronics in this little building. So the data acquisition system is going to collect all those waveforms, do initial processing with a cluster of around 110 cores, and then there's software filters that are going to reduce the rate from 2.5 kilohertz, or about a terabyte of data per day, down to various different substreams that are allowed to be overlapping. They target different particular physics possibilities that are never more than about tens of hertz or 100 gigabytes a day total, which is basically all we're allowed, because we have to send this filtered data back over satellite to the University of Wisconsin-Madison for additional processing. That is a very finite bandwidth resource. So that's where we are starting with getting the data. Now I want to talk about some statistics, and in particular, maximum likelihood methods, which are kind of the foundation for our work. So we start with waveform decomposition. Sorry, this is a little bit hard to see on screen, but what happens here is we have 4 digitizers. So there's one that samples continuously, but kind of slowly. And then there are 3 more that are faster, but they can only run in short bursts at once. These are in 3 channels that have different gains to improve the dynamic range. So you can kind of make out here, there's these binned waveforms. You can see maybe some of this noise here in green. I had to pull this from somebody's thesis. We really prefer not to talk about this, but I thought you might like it. So we use a non-negative least squares method to fit these binned waveforms with pulses that just have a pulse arrival time and a pulse height or total charge in photoelectrons. And so these pulse series are actually the inputs to all of our event reconstructions. So data reduction is the theme here, right? Like we said, so we need to decompose this waveform, and there's going to be more steps like this. Here's a more complicated one, and I think also, for some reason, a better color scale. And you can kind of see how we have all of these individual fitted pulses, and if you refold them back into what kind of waveform they should mean, they do basically fit the binned waveforms that we were starting with. So this is the geometry that we need to consider if we want to go from all these individual pulse series to one set of coordinates and momentum for each individual event. So let's say we've got a muon that's passing through in the vicinity of our detector, and there's an optical module over here. You can tell this is a very old picture because it doesn't say DOM, it's just optical module. So the Cherenkov light is going to come out at this fixed angle theta c, and that angle is determined by the local index of refraction, like we talked about before. It's sort of like an optical boom analogous to a sonic boom that you might have already seen before. So the event reconstructions are going to use increasingly detailed hypotheses to try and model this situation and find this trajectory and the parameters of it that are going to result in photons being as likely as possible to have arrived when they seem to have arrived. So we start with something that's completely unphysical. We call it line fit, and here we're assuming that theta c is 0. So all the light is just traveling in a plane along with the moving particle. And we have some DOMs, some set of DOMs I, which observe signals. So what's nice about this is because we've made this unphysical assumption, we get a very simple answer. So now we have this position and this velocity fixed for some choice of time, which is degenerate, because it has the speed. Anyways, so you get these parameters, and this is totally unphysical, but it's pretty close. And so this is able to be used as a seed for the more advanced reconstructions that actually try to model the physics that's really happening, but those are harder to find the global optima, so you need a good starting point. So the next step is this single photoelectron search, and this is fit, and this is where we start using maximum likelihood methods. So the likelihood, we also saw this earlier, it's just a product of probabilities. So here the product is overall of the individual DOMs, and you're trying to find the coordinates and travel direction that make it the most likely to have seen the light pattern that you saw. But for SPE, we're assuming that there was only one photoelectron per DOM, and that photoelectron arrived at whatever time the first one that DOM saw one was. So you just look at the first one, and you also assume now that we're only looking at things that are traveling at exactly the speed of light instead of trying to fit for that. And in practice, those are the only interesting events, are the ones that are going right around the speed of light. And we use this Handel parameterization, originally published in a German thesis. Good luck going to the original source, but it looks something like this. You have some time delay and then some probability of getting that first photon at that time. And so if you multiply all those out and then you use a fitter, you can try to find the event's coordinates and direction. Then we can move on to some more advanced reconstructions. And so this is what we do. So we're still using the same likelihood, but now we improve these factors P over here. So first we do a multiple photoelectron fit, where we're saying, okay, we know that we're still only going to look at the timing of the first pulse, but now let's consider how likely that was to have actually been the first pulse, given how much charge we saw overall, which is still kind of hand-wavy and magic, but it does work better. Then we can use the spline MPE reconstruction, which is like the regular MPE, but more realistic. So we're using a spline fit to the true absorption profile and the true scattering profile that have been measured in the ICE over the last several years trying to model this, rather than using the parameterization that we hold constant throughout the entire ice cap. And then finally, we have this most advanced reconstruction, millipede, which tries to reconstruct the entire pulse series. So you try to fit all of the timing, not just the initial timing and the total charge, which is the best that we can do so far, but it's much more expensive. And so most of our analyses can't actually use it for all of the events. So now I'd like to talk a little bit about machine learning and IceCube. And so far, this has all been very classic statistical physics, but here's our problem: the cosmic ray muon background. We talked about it a little bit already today. We definitely tried. I mean, we went 1.5 kilometers down before we even started building the detector. There are still so many cosmic ray muons there. We're looking at the highest energies, and we have a huge detector, and we're getting a factor of 10 to the 5 more of these cosmic ray muons than we are atmospheric neutrinos, and then even another large factor before we get to the astrophysical neutrinos that are quite rare. So if you're at the South Pole and you try to look up, you're just going to get all of these cosmic ray muons, and most of them are well reconstructed. And you can say, okay, I know that was coming from the sky, so it's probably not a neutrino, it's probably a cosmic ray muon. Whereas if you look through the Earth, so things that are upgoing for somebody standing at the South Pole, neutrinos are the only thing that can get through. If you can find the well reconstructed northern muon tracks, then you know that you have neutrinos. But since there are so many downgoing cosmic ray muons that can pull the reconstructions, maybe less than 1% of the time, that's still enough to swamp your analysis. So that's where it's going to start getting complicated. So these methods are good if you're willing to look at the north sky and new mu only, because we can find the new mu's that interacted outside of the detector and just got to us eventually. The alternative approach, I want to throw this out there because I did want to mention some of our results, and our best ones actually come from this method, is to use an active veto to select starting events. So here we're saying, let's throw away the outside of the detector and also this kind of weak part that's, very dusty layer in the ice cap. Anything that puts its first light in that region, we say, okay, we don't want that. It's an incoming event. It's probably from a cosmic ray. But if a neutrino sneaks through this veto and then interacts, and then there's a charged particle that's producing light, we can keep that. So this is a way to do a full sky and all flavor analysis. You can see the tracks and the cascades, any flavors, but the reduced effective volume is significant, because now we can't take the upgoing ones that came from wherever and got to us eventually. We can only take one starting in the detector. So we like to be able to identify these well-reconstructed northern tracks and tell them apart from misreconstructed particles that really were downgoing but tricked our reconstruction. So this is one of a few examples I'm going to show of how you can do this. So first we can look at the line fit speed. So that's our first reconstruction. We fit the speed, but we know that if it was an interesting particle, it's actually going at speed c. So let me break this plot down a little bit because there's a lot going on. First, we've got this separately normalized curve in blue, and this is our signal Monte Carlo. And we see that it's sharply peaked right around 0.3. I'll read it for you because it is a little too small, but that's in meters per nanosecond, somewhere around there. And so this is sharply peaked right around the speed where you should actually get it if it's a good reconstruction. But all of this junk that leaked through the initial software filters, this is simulated cosmic ray muons, and then real data, which is mostly junk at this cut level. We see that the peak is in a different place, lower speed, much more spread out. So this is one handle that we can use to discriminate between good reconstructions and garbage. When we go to the likelihood reconstructions, we also have another really powerful handle. So here, this is the reduced log likelihood, which is the negative of the log of the likelihood divided by the numbers of degrees of freedom of the fit. And so what we find is that you get smaller values, so it's minus log likelihood, so higher likelihoods, smaller this thing, for the signal hypothesis, and then all of the junk tends on average to have these sort of higher values. So that's one more handle. And we can also look then at fit agreement. So let's say we have the line fit, and then we have the more advanced reconstruction like NDE, they should still be pretty close to each other if the event was nice and data. So we're looking for a peak in our signal that's going to be very close to zero separation between these two things. And then all the junk tends to have like some garbage line fit and some garbage log likelihood reconstruction that doesn't really have as much to do with it. So we can use all of these. We can use other parameters that are also based on these reconstructions, like number of DOMs that were very close to the reconstructed track that had hits on them, stuff like that. And so we can construct all these parameters. And in principle, those would be enough to select good neutrino candidates. I mean, we have all these different features, and you can actually get a very high neutrino purity sample by just making a few simple cuts on those various variables. The problem is that only the best events will remain. So if you have a really bright event, maybe something is weird about it, something's not in the sweet spot of the parameter space, even though everything else is technically completely fine. You don't want to just throw that event away. So machine learning outperforms for both signal efficiency and it turns out also for background rejection. So we want to synthesize all this information and get a little bit more efficient with our selection. So for IceCube, the main approach that we use is decision trees. So we really like these a lot because at any given spot in the process, you're just making simple binary cuts, which is what we do all the time anyway. Physicists don't get weirded out by this kind of thing. So just a quick review of decision trees. I feel like maybe people are probably familiar, but so what happens is you can have an event with some parameters, you put it here and you say, okay, if it has this parameter smaller than this value, send it left, otherwise send it right. And you do this recursively until you hit some leaf somewhere, at which point you can assign a signal or background probability for that particular sample. The way you construct it is using a supervised training procedure. So you have some signal set, some background set, and you say, I know in advance that that's what these are. And you recursively apply the best split available until you get to some maximum depth or some purity cutoff or whatever, then you stop. For the choice of data sets, we're going to use signal Monte Carlo here basically every time for the signal data set. But for the backgrounds, we can either use background Monte Carlo or we can use the real data itself. These methods tend to be pretty robust against a little bit of signal contamination. So it's okay that there are atmospheric neutrinos in our real data, as long as they're much more rare than the stuff we really want to get rid of, which is like cosmic ray muons and all the weird ways that they can interact in the detector.
What are these predictors?
So I guess you mean like which features are we using? So these were supposed to be some examples of the kinds of things that we would use. So like things that come out of the reconstructions, like the speed, the fit speed, and the reduced log likelihood and all of that. There are a bunch more, and different analyses kind of tune these things independently. Actually, this is like the theme that's going to emerge here is that IceCube is trying to catch up with a world of people really understanding machine learning, but physicists tend to be rather conservative about this sort of stuff, at least in this field. So right now, there's not like a standard way where everybody's doing the same thing. It's kind of a lot of different grad students that are all trying to do their analysis the best they can. They're all a little different. So let's see. Yeah, so that was decision trees. We can't just use one though. If we try to make one decision tree that had enough information to do a good job for some data set, then another data set that was statistically comparable would not get good performance. So we're going to get much better results if we're averaging over hundreds of trees. So this is what we do. You can induce this variation between the different trees by one of two ways. You can boost the weights of misclassified training events. So if I didn't get it right with this tree, try a little harder to get it right on the next tree. Or you can randomly restrict the training data sets on a per tree basis or the training features on a per node basis. Or I think maybe this is somewhat unconventional. I don't think I've really heard of people doing it. People have given me funny looks about it occasionally, but you can do both of the above. And it seems like that kind of works and it reduces overtraining a little bit in some cases. And so this is something that we have done. So this is a plot from my thesis where I'm trying to find high energy neutrinos that could be coming from gamma ray bursts. And what we find is another one of these plots that just has like a blue thing and everything else somewhere else. That's exactly what we want. The point is that this one is better than any of the individual ones that we saw in previous slides. So we synthesize all of that information into one powerful feature that we can then cut on to obtain a signal sample. And so to get the final selection, you might just apply just one more cut on this parameter. That was what I did. We play a little bit fast and loose in the GRB group because it's a very low background search. We're looking for these massive explosions that take like 1 second and we know exactly where they are. So there's no background. But if you're trying to look at the whole sky at once, maybe you're going to be a little bit more careful. So this was for measuring all of the fluxes, atmospheric and astrophysical. I know that this is a little bit small, so let me just point out what's going on here. So this black line on each of these is the cut as a function of the classifier score and the cosine of the zenith angle. So the top of this plot is if you were looking straight out through the side of the ice cap from the detector. The bottom of each one of these is if you were looking straight down all the way through the North Pole. So through the other side of the Earth. And so because the various backgrounds have different behavior looking in different directions because of the different amounts of Earth and ice that the various things are passing through, you might want to make like a slightly more complicated cut like this. And so what this is doing is it's retaining most of this signal flux, which they were looking for new muons coming from space. You can reject atmospheric muons, and you can also reject atmospheric neutrinos that are causing neutral current or new E's. So this is basically the kind of thing that we do, and it hasn't really gotten much beyond that in terms of machine learning for IceCube yet. I do want to talk about some software considerations. So how are we actually getting this work done? When I was a grad student, as I was learning the ropes, TMVA was the library that was being used to sort of the de facto standard within IceCube, and I think probably elsewhere in the field. It depends on a library called Root. You may have heard a little bit about Root. My friend Rachel Tony talked about it a few months ago. This is a, let me say, very questionable C++ library. Physicists maybe don't realize what's wrong with it. Now, even with PyRoot, which attempts to make it a little bit more handleable, the usage was not exactly what I would call Pythonic. So I was pretty disturbed by this, and I didn't want to have to like work around these issues by dumping my data in text files. So I started looking for alternatives. At the time, scikit-learn was still relatively new, at least as far as I can tell, at least according to like Google. So I saw a bunch of different alternatives, RapidMiner and various things, all these different interfaces and different languages. Nothing really jumped out at me as like, this would make perfect sense in IceCube's Python and C++ software stack. So my custom implementation, PyVDT, was born. This is kind of our new de facto standard in IceCube. It's not the only thing being used, but much more than I expected when I wrote it. But is it worth it though, having another library? I mean, okay, so now I know that scikit-learn provides a ton of great tools and like also just that it exists. And some people have started using it. So now at this point, we're kind of unsure about the future of this custom library for us. But I will note though that it has some advantages. So this was written kind of, by us, for us. It's not, let's be as general as possible. So one thing that we do that I think is actually a good idea is that the models insist on carrying around feature names from the start all the way to forever. And I think this is useful for collaborating compared to dumping all of your data into one giant 2D array, and then maybe you might lose track. Or maybe you have to write a custom wrapper every time to make sure you don't. The other thing is that there are bundled tools, so everybody's making the same plots. So, like I said, physicists are very conservative, and maybe when our advisors came up 10, 15 years ago, whatever, they didn't really know about this stuff at all. And so it helps that they can learn it kind of once and then see similar plots every time they do a similar analysis review. They don't have to start over and be like, what am I looking at? So that seems to kind of help. I've heard good things about that. And the last thing is we have full control of the code, which is sort of a burden, but it also helps in the sense that we can have confidence in the stability of our results. So for example, there was recently what they called a bug fix in scikit-learn, where an arbitrarily small number was needed to avoid taking geometric means with zeros in them. And they changed the hard-coded arbitrary small number, which meant that all of our safe classifiers were garbage unless you recreated them or relearned what the distributions were going to look like with the new versions. We can't really deal with that if we're trying to have somebody do some work on a classifier and then use it again in the future. I mean, maybe we can just not upgrade. That's what they did. But now they're graduating. Do we keep using their work? What do we do? In PyBDT, we made a scikit-learn import with a toggle to use the old behavior or the new behavior. So now they don't have to retrain the classifiers anymore. So I don't know what's going to happen. There's a GitHub release planned for this code. It's really just like a technical matter of how do we get it to still work with our system, but also be sane on GitHub, because we have like a kind of weird directory hierarchy, you know, that kind of stuff. But it's gonna go out there, and you know, we'll see what happens. So that's all I want to say about machine learning. I should give some neutrino astrophysics highlights, because that's sort of what IceCube is about. So I'll remind you the active veto method. In the simplest method, you just have this very thin layer, and you can be sensitive to all flavors of neutrinos above 60 TeV, which is much higher energy. We're talking about like hundreds of MeV before. Is that right? There's like MeVs and GeVs in your talk. So this is like, you know, 1,000 or thousands of times more energetic or more.
Mostly MEV.
Mostly MEV. Yeah, which I think you referred to as kind of high energy.
For us, it is.
Right, so this is a very different regime here. So we're looking for very rare events. So what we found, oh.
Attenuate features, or have they always been?
So I guess they're redshifted in the same sense as anything else that happens in space would be redshifted if it was far enough away. But if I think we're expecting neutrinos from things that are close enough that that redshift wouldn't be a huge change. I hope that's accurate. Something you do have to look out for that I guess I did gloss over here is that at the highest energies, the cross-section actually does grow. So you can't look directly through the Earth for the highest energy neutrinos. You have to kind of look at the horizon where there's a bunch of ice enough to catch them, but not enough to guarantee you that you can't see them. So that is something to look out for. But okay, so this is probably our most important result so far. The high energy starting events resulted in a 4-year sample with 53 events. This is appropriate. I'm actually wearing one of them. You guys will see it later. Probably the most famous individual neutrino that I'm aware of, and 52 others. And so this represents, if you look at the distribution of deposited energy, this counts versus deposited energy. The black is the data, and these shaded regions here are the expected backgrounds. And then this is a fit to a potential astrophysical signal. This is the fit that we get, and it's a 6.5 sigma fluctuation above the background that was expected based on, again, a maximum likelihood forward-folding method. Same kind of measurement we've been talking about all day. So this is considered discovery level in particle physics. I guess 5 sigma will be the discovery threshold. So we published this. No Nobel Prize yet, but we did get Breakthrough of the Year. Somebody assigned that award. Physics Breakthrough of the Year. The journal put it out. I really should have remembered who exactly said it, but I don't know. No Nobel Prize though, so not yet. We have double-checked this result. I want to mention this one, even though the muon neutrino version of this analysis hasn't reached the 5 sigma threshold by itself, but it does sort of confirm the same results. So again, here we're going to accept incoming tracks now. So higher effective area or bigger effective detector. We can only look at the north sky. We're going to look at somewhat higher energies. we're going to have a high efficiency selection from machine learning. That two-dimensional cut that I was showing earlier was actually for this analysis. So we get a sort of similar best fit spectrum here. These are just like the cosmic rays, right? So it's e to the minus something, and then some normalization. They're both kind of around what we would expect if the neutrinos were associated with the cosmic rays, but they're inconsistent with each other at about the 2 sigma level, which we don't understand. It could be because we're probing different energies, or it could be something else that we just don't get yet, we can't resolve. So that's kind of the status of the astrophysical neutrinos. And I have a bunch of things on the searches for sources, but we haven't seen any yet. So I figured I'll just leave those in the backup slides in case anybody's curious. One other thing I want to talk about is that we're not actually done with this yet. So IceCube Gen 2 is a proposal for a 10 times bigger detector, so 10 cubic kilometers. This is sort of an artist's impression. The layout is still being optimized. It would be the same kind of deal, double the number of strings, space them out more, grow them in the direction away from the geographic South Pole, where we're allowed to build potentially, and a little bit less regular than the original grid. Another idea that I think is great, but also really ambitious in terms of actually getting it funded, if this is the footprint of IceCube, build this huge surface array. So you have, instead of the Vito being down there with you, you have the Vito on the surface of the ice, and that way you could do the same trick we were talking about, accepting incoming tracks. The neutrino can interact anywhere, even if it's coming from the southern sky, and you can still catch it because this thing helps you know that a cosmic ray wasn't involved. That would be great for looking at the southern sky, but hopeful, but I don't know. And then the last thing is Pingu is at the other end of the energy spectrum, so totally different scale now. These black dots and the red dots are existing hardware, and then this blue infill array is much denser, and it would increase the low energy reach, which would help for studying certain kinds of fundamental physics, getting back into the neutrino oscillation kind of material. So I have 2 summary slides. This is the one on physics results. We have started what we've discovered, and we've started to characterize an astrophysical neutrino flux. So far, we don't know where it comes from, but there's new methods being developed. There's multi-messenger collaborations with other kinds of observatories for like gamma rays and X-rays, cosmic rays, whatever. So we're working on all of that, but nothing yet. But we're also working on a next generation of detectors that will be significantly larger and more powerful. And so this could be an unprecedented window into the universe. On the data science side of things, well, physicists are really we're kind of consumers of machine learning technology. I don't know that in particle physics we've innovated particularly much on this. And so decision tree forests are probably just the tip of the iceberg for us. I mean, what about neural networks? They seem extremely promising almost everywhere they come up. And maybe with the right training, we could throw away all these likelihood reconstructions and just ask the computer, what does this look like? Where did it come from? I don't know. We haven't done it yet. But what I do know is that it seems like data science innovation is going to trickle down to us eventually. So keep on innovating, and then we all profit. So that's it. Thanks.
Thanks, Mike. We have time for questions if anyone. We're exactly on track with 5 more minutes left. So if anyone has- yeah, please.
Was thermodynamics part of when you go down, the temperature theory. Was that ever put into change causing the flux?
What was the question?
The temperature.
Yes.
Temperature factor. Was ever looked at?
In case of solar neutrinos, it does affect the reaction. Actually, the flux of neutrinos comes from the sun. Does tell you something about how the sun works internally and how the heat is produced there and where because when I talk about solar neutrinos, I say just like neutrinos, but in fact there are several reactions. that happen there. It's a whole chain of reactions. Those reactions happen in different regions of the sun. And by detecting different fluxes of different reactions actually tells you how the whole chain happens and how the whole production of the heat and propagation that it comes.
What about the one below?
The Earth. So it's warm there, but it's warm in the. It does not affect us. In not the physics results. It gets quite warm down in the mine itself, but that has to do with the operations of the mine. It's 2 kilometers is not enough to get.
Yeah, so we're pretty deep, but it's in the ice cap, so it's cold. We have to cold test all the equipment to make sure it's fine, but the local cold doesn't seem to affect us too much. There is an interesting effect with atmospheric, so cosmic muons. Depending on the time of the year, the atmosphere kind of like expands and contracts, and this can result in different rates of muons that penetrate all the way into the detector. The Drexel group actually, we had some undergrads doing a summer study on whether this was also observable in atmospheric neutrinos, and we haven't seen it yet. It was kind of statistically limited. So,
There's very little like temperature dependence in these hard guys. It's mostly the same temperature effectively, almost nearly to like actual content.
should also, there's a gradient, right? But it's pretty slow.
Yeah,
So it's like
it's
minus
very-
50 C at the surface and right around 0 all the way down. But in the part where IceCube lives, which is mostly the part that's closer to the bedrock, it's pretty consistent around there.
Yeah, it's pretty close to 0. Yeah, it's just
Yeah.
like slightly below 0.
Yeah. In snow, there's also the thing is that since the whole detector is submerged in water, we actually cool the water to maintain constant temperature because the instrumentation itself is sensitive to temperature. The efficiency of the photosensors fluctuates with it. So we, even though it is the temperature itself does not affect the physics results, it can affect instrumentation. So we make sure that the water stays always at it's about 20 degrees Celsius. No, it's actually
15.
a bit below. So in snow it was a bit warmer than it is now. But we maintain it at a rather constant temperature because the efficiency of the increase of the sensor is affected by this temperature.
So it's keeping your calibration valid.
Yes.
Like if you can calibrate continuously, you wouldn't have to.
Well, we did do a test, a temperature test on it, and the drift is not big, but it was not small.
Any other questions, comments?
For IceCube, do they have any idea that that mysterious layer of dust was there before they built it?
No. Yeah, I was like I worked on IceCube for like originally a long time ago, and
They found that during the Amata days, right?
yeah. Well, I mean, they originally found they didn't think it was like it would be that bad, nothing. So, and instrumentally, right? Instrumentally, they couldn't have. The design was already in place, and then they didn't think it would be as thick or as that, and so, and there's really nothing they could do about it.
There was one small adjustment. So if I can get back to the, let's see, I'm not sure you can make it out here. Yeah, you can kind of see it. So the deep core infill detector, you can kind of make out how there's 2 cylinders that are highlighted there. There's a gap. That gap is a dust layer, and I think they just left that part out of the instrumentation.
Yeah, completely.
Right, but the other strings are instrumented. But the deep core was like one of the last ones deployed, so I think they tweaked the design to make sure that they wouldn't waste DOMs.
Any other questions? Comments? Well, with that, thanks, Mike and Nuno again.
Before I release, first off, thanks to Penn Physics for hosting the event. Thank you, Sean, for getting speakers all lined up. It was two great talks. Thank you to Healthverity for sponsoring the food. We had a lot of open positions available, so check out healthverity.com. I'll also be available after. I think we're going to go to New Deck Tavern. If you guys want to get together for a drink, I'll be available. Reminder for next week, Tuesday is a data-thon, Wednesday is what's that called? The super meetup. And September, we're still maybe looking for a second speaker. We think we have one lined up for sure, but we're still looking for a venue, I believe. So if your company would like to get involved with our community and has an ample space to hold about, at least max like 70 people, please get in touch with one of us, any of us. Always looking for new venues to explore and for new companies to kind of help develop this culture that we started with this group. And that's it, Mike, right? All right, so New Deck Tavern is, walk west and half block north. It's block. Between 34th and 35th. Next slide. So I'll be there. Feel free to come to me. Thank you.